Okay, students, let's go to question number 17. Here, I'm going to introduce you a certain operator. The product operator, pi, is defined as pi of, you see, n running from 1 to k of uk is defined as u1, u2, u3 times it goes on up to uk. So here in between this, we are considering time multiplication, okay? So we are going to multiple this k different terms from u1 up to uk. u1 times u2 times u3 times u4, it goes in such a way up to uk. So the product operator pi is defined this way for some sort of natural number k. Now, having this into account, you are asked to find the value of this one, students. The value of this product operator times log of n plus 1 to the base n. So to find the value of this, what you need to do is you have to have this one, okay? First, let's write this one, students. Let's write this one. This starts from n2. So this is going to be logarithm of 2 to the power of 2 plus 1, 3, right? Logarithm of 2 to the power of 3. Logarithm of, now again, put 3 there. Logarithm of 3 to the power, logarithm of 4 to the base 3, logarithm of 5 to the base 4, logarithm of 6 to the base 5. It continuously moves in such a way, okay? As we defined this product operator. So if n is 2, look, it starts from 2 and it goes up to the power of k minus 1. So the last one is to the power of k minus 1. But before that, we must have, you see, to the power of k minus 1 minus 1, which actually is to the power of k minus 2. So here, look, log of to the power of k minus 1 to the base 2 to the power of k minus 2 is used because the number less than the number less than to the power of k minus 1 is to the power of k minus 2. That's why I'm having here to the power of k minus 2 to the power of k minus 1. Now finally, for the to the power of k minus 1, we are going to have to the power of k minus 1 as it is, but as we are increasing this to the power of k minus 1 by 1, we will never have this minus 1 and then to the power of k can come. So everything will be written as you see. Look, logarithm of 3 to the base 2, 4 to the base 3, 5 to the power of 4. So everything here is increasing by 1. Here also everything is increasing by 1. So from to the power of k minus 1, when you just add 1, you do have to the power of k. From to the power of k minus 2, when you add 1 to the power of k minus 1 is obtained. So everything is now labeled according to its what? Pattern. So the next task is to recall this one, student. You have to recall this. Logarithm of b to the base a times logarithm of c to the base b is the same as this one. Look, logarithm of b to the base a can be written as 1 over logarithm of a to the base b. I interchanged these two. If you interchange this, you can have this one. But here we have logarithm of c to the base b. So this is the same as this one. 1 times logarithm of c to the base b is logarithm of c to the base b, and this has to be divided by logarithm of a to the base b, as you see. So the bases are the same, so now this is going to be logarithm of c to the base a, and we call this base change, right? The bases are the same, so we can take logarithm of c to the base a. This is one property of logarithm. This is true. So from this you can understand that whenever you are given this kind, you can, as long as these two are identical, you can cancel this by this, and then log of c to the base a can be obtained. You see, have attention here. Whenever you have such kind of, you see, way of expressions, look, b can be cancelled by b, and then you can take log of c to the base a, okay? Log of c to the base a. The final output shows that this one is true. The same is happening here. Look, we can cancel 3 by 3 as we cancelled b by b here, and then you can have logarithm 4 to the base to 4, for instance, the first two here. But look, this is continuously moving in this way, so these two can cancel each other, these two can cancel each other again, these two can cancel each other again, these 6 can be cancelled by the one, you see, which is to be written next. In such a way you can cancel one over the other, and when you come to this, look, these two can cancel each other. To the power of k minus 1 can be cancelled by to the power of k minus 1, and the one here to the power of k minus 2 can be cancelled by the one before it, okay? So the final output will be logarithm of, you see, to the power of k to the base 2 is going to come, okay? So logarithm of to the power of k to the base 2 can come. That is to say, this expression is the same as logarithm of to the power of k to the base 2. So using logarithm property, this k can come in front, and then k times logarithm of 2 to the base 2 can come. And we know that logarithm of 2 to the base 2 is 1, so the value of this is 1 times k, which actually is k. Thus, this expression is the same as what? K. So having this into account, what comes next is, you see, question number 18. You have been given that, you see, f of x is x squared minus 4 over x squared minus 2. So you are asked to determine x squared minus x minus 2. You are asked to determine the following, okay? So here, the first question is to find the domain, and next, you are asked to find the intercepts. And next from this, you are asked to find all the existing asymptotes. And finally, you are asked to sketch a graph of the function. So this is simple, guys. What we need to do is the following. The domain of a rational function is nothing but it is, you see, the set containing those values of x that can make your function defined. So try to consider the denominator. Those values that can make the denominator 0 must be excluded. So the domain is the set containing x such that, you see, the denominator is free from 0. That's why I wrote here x squared minus x minus 2 different from 0. And from this one can obtain that, you see, think of two numbers where their sum can be -1 and the product -2. These two numbers are -1 and 2. So this can be factored as you see x minus 2 times x plus 1 different from 0. Now solving this, you will obtain that x such that x is different from -1 and 2. So whatever number you may take except -1 and 2, this will have a meaningful output. So the domain is, you see, in terms of interval this kind, or you may also consider a set of all real number without -1 and 2. Okay? Now this is all about the domain. And coming to B, it says find the intercept, students. How are you going to find the intercepts? We do have two intercepts, x and y. So in order to find the intercepts, what we need to do is the following. Let's find first the x-intercepts. The x-intercepts for this can be obtained as follows. Okay, f of x equals 0. You see, the x-intercept is obtained by making y 0. So make f of x to be 0. So x squared minus 4 over x squared minus x minus 2 can be factored as you see. X minus 2 into x plus 2. X minus 2 into x plus 1, because x squared minus 4 is the same as x minus 2 times x plus 2. And here x squared minus x minus 2 is x minus 2 times x plus 1. So now look, x minus 2 can be cancelled by x minus 2, and then this is the same as x plus 2 over x plus 1. This is true provided that, you see, x is different from what? X is different from 2. And then x plus 2 over x plus 1 equals 0 is going to come. Now it's from this that you need to determine what, students? The x-intercepts. So the x-intercept can be obtained by looking for the value of x that can make this 0. And this is obtained as x plus 2 equals 0, x equals minus 2. So we have x-intercept of the graph at minus 2, okay? At minus 2 only. At 2, instead of having x-intercept, we will have what? A hole, because 2 is, you see, the 0 of both the numerator and the denominator. In this case, we have a hole rather than having intercept, okay? Anyway, the x-intercept is obtained to be minus 2, 0. This is the x-intercept, okay? And when you come to the y-intercept, we need to substitute x to be 0, directly put 0 there. So 0 minus 4 over 0 minus 2 is going to come, which actually is what? 2, right? So the y-intercept is at x0, y2. Now proceeding to the next one, since 2 is the 0 of both the numerator and the denominator, as I said earlier, you see, because when you substitute 2 here, it will be 0. Again, if you put 2 here again, it will be 0. You see? Then at 2, we do have a hole, okay? If this happens, hole exists. And at x2, y is going to be, you don't need to substitute that 2 here in place of your function here, okay? In x of your function, because it is undefined already, but here it is simplified. You see, it is simplified. So at x equals to 2, 2 plus 2 over 2 plus 1 is going to come. 2 plus 2 over 2 plus 1. And this is 2 and 4 over 3, you see? So the point, at the point 2, 4 over 3, we have a hole, students. We need to have a hole there, okay? By the way, if you didn't have a hole here, you see, the graph of this is not the graph of this one, okay? Or the graph of the graph of this one is not the same as the graph of this one, okay? What we are going to do is we are going to sketch the graph of this function, f of x or g of x equal to x plus 2 over x plus 1. And so long as you are having this hole at 2, 4 over 3, this graph will be the graph of this one, not the graph of this one. If we are not going to use this hole, it will never be the graph of this, rather it will be the graph of this one. Mind you, our intention is to sketch the graph of this function, not this one, basically. So the difference between these two graphs can come when you put this whole at the specified place at 2 and 4 over 3. That is the idea, okay? And when you come to the asymptotes, here we have a vertical asymptote, and the vertical asymptote is existing at -1 because at -1 this is undefined, okay? This is undefined. Not only that, this is also undefined at -1. And then at x equals -1 we do have a vertical line where the graph never touches it. And here, as we are approaching to -1 from the right, y goes to infinity, because as you are approaching to -1 from the right, you are using numbers like -0.9. Here, -0.9 plus 2 makes positive, and again -0.9 plus 1 makes positive, so the ratio of two positive values makes positive infinity. And as x approaches to -1 from the left, you are using -1.0, something like that. -1.0 something like that plus 1 makes negative number, and here -1.0 something like that plus 2 makes positive, so positive divided by negative is negative, so y, or the graph, you see, sinks down as you see, minus infinity, okay? So as can be shown here, we do have two asymptotes, vertical and vertical asymptote and the horizontal asymptote too, okay? The horizontal asymptote is going to be y is equal to 1, because as x goes to infinity, y approaches to 1 from above, and again as x goes to minus infinity, y approaches to 1 from below. The case is when you divide x plus 2 by x plus 1, you do have 1 plus 1 over x plus 1. Just apply long division method. X plus 2 divided by x plus 1 is 1 times, and 1 times x plus 1 is x plus 1. So as you are subtracting x plus 1 from x plus 2, the remainder comes to be 1. So we are having 1 plus 1 over x plus 1, as you see. So as you are having large number, you see, in place of x, you see this will be a small number. Even if it's a small number, a positive small number, it will be added on 1. That's why we're having here 1 above. But as you are moving to negative infinity, you see this is going to be negative number, because negative infinity plus 1 is negative. So negative number is going to come. Even if it's a small number, it will be deducted from 1 because it's negative. So it will be, you see, approaching to 1 from below. You see, 1 from below. Dear students, as a tip, let me just tell you one important thing. The graph of rational function never crosses a vertical asymptote, okay? But there comes a case where it may cross horizontal as well as oblique asymptote, because the concern is what is going to happen to the graph as we are moving away from the y-axis, okay? That is the idea. Now, proceeding to the next one, let's see the graph, how it looks like. Look, students, as can be shown, the graph looks like this one. Look, the vertical asymptote, as you see, is at x equals 3. It is already, you see, represented as can be shown. At x equals 3, we have a vertical asymptote. And the horizontal asymptote is at y is equal to 1. Look, it is at y is equal to 1. And the whole exists at -2 and f g of -2. So look, at -2, we are having a hole. So it's undefined at here, okay? So this is the graph of the function. So as you see, as x gets larger and larger, you see the blue curve, it gets closer to the x-axis. The same happens to the left side. So as you are moving to negative infinity, the blue curve gets closer to the line y is equal to 1. So y is equal to 1 is the horizontal asymptote. Coming to this, as you are approaching to 3 from the left, you see the blue curve sinks down. You see it goes down, as it can be shown. And as you are getting closer to 3 from the right side, as you see the blue curve rises up. That's why we're saying that as x approaches 3 from the right, the function or y rises up. So this represents the graph, right? So what can you say about the domain? The domain is a set of all real number except what? Except at -2 and 3, because at these 2 points, you see, our graph is not plotted. It's undefined. What can you say about the range, students? The range can be what? Any sort of real number except what? Except -1, because at -1 it's undefined, as you see. No value makes the output to be -1. You see, as can be shown, we are having a horizontal asymptote there. This is all about what? The graph. Thank you very much.